The moon is Earth's only natural satellite. It has no atmosphere to speak of and is covered in craters caused by asteroids smashing into it over billions of years. But what if we put a pull on the moon? How would that work? Would it float? Well, it turns out that there are a lot of problems with this idea, but there are also some fun physics problems to think about. First of all, we can ignore most of the craters because the surface of the moon isn't really solid. It's covered in a layer of regolith, which is a loose mixture of dust, broken rock, and other materials that make up the top few meters of the moon's surface. Underneath that is a more solid mantle, but we don't have to worry about that because the weight of the pull and its contents will only affect what's below it on the surface. So let's assume that our pool is resting on a nice flat bit of solid ground, one that's not moving due to the moon's tectonic plates shifting around. Because even though the moon quakes happen on a much smaller scale than earthquakes here on Earth, there's still plenty of moon shaking going on. The next thing we need to think about is how water behaves in zero gravity. Now, astronauts aboard the International Space Station experience weightlessness because they falling around the Earth at the same rate as the ISS. The two are freely falling together. But things don't behave the same way on the moon. To get to the moon from Earth, a spacecraft has to speed up and break free of Earth's gravitational pull. So once the pull is on the moon, it's not falling at the same rate as the moon itself, which means it won't just float around. Instead, it will slowly drift upwards. That's because the side of the pull closest to the Earth will experience a stronger gravitational pull than the side of the pull furthest away from Earth. This difference in gravitational pull will cause the pull to very slowly move upwards over time. And that brings us to another problem. If the pull is drifting upwards, then the water in the pool is also drifting upwards. In zero G, water doesn't just form a nice spherical shape. It actually forms these cool, kind of creepy spikes. They recall the eutectic minimum, and they happen because there is no force overcoming the cohesive forces within the water. So instead of floating around like a balloon full of air, the water forms these cool spikes, and the whole structure floats upwards very slowly. Now, at this point, you might be wondering why we do and see these weird water formations in space when astronauts go swimming. And that's because the ISS astronauts are in 16% Earth's gravity, not zero gravity. So the water still feels a small gravitational pull towards Earth. But when you're on the moon, you only feel about 1/6 of Earth's gravity. So the water isn't pulled down into a spherical shape by gravity, but it is still affected by gravity, and that leads us to yet another problem. Water on Earth boils at 100 degrees Celsius, but that's only because of the surrounding pressure. When you remove the pressure, like you do in a vacuum, water boils at about 30 degrees Celsius. A good thing too, or else we wouldn't be able to have hot drinks in space. But because there's no pressure on the moon, every single drop of water in our pool will boil and turn into vapor. That means our water pool won't stay a pool for very long. But assuming we can keep the water in liquid form, we now have another problem. Light reflects off the surface of the water in the pool, and if we look at the moon through a telescope, we can see these weird light patterns caused by pools of reflective material. So if you wanted to hide your pool on the moon, you wouldn't want it to be a bright white color. You would want it to be a dark color so it absorbs the light and doesn't reflect it back to telescopes on Earth. In conclusion, putting a pool on the moon is hard. Can it be done? Probably. Do we want to? Probably not. If you like learning about all the ways that a pool on the moon wouldn't work, then you'll probably like this course on solar energy. It covers everything from basic concepts like how light and heat work to advanced concepts like how concentrated solar power plants generate electricity. And best of all, it's completely free. Just like all brilliant courses, it's interactive with follow-up questions after each section to check that you understand the concepts, so go over and check it out.